rich in knowledge. I don't know about monetary
Or maybe just famous.
value, but
Okay. So after the mini lecture, I'm gonna split this into groups, into 4 groups. You can choose to do the same group in the lab. You know, it's up to you. The nice thing I think, as a group, you did learn how to use the instrument. So, but everybody did that, right? So it really doesn't matter.
Yeah.
In terms of logistics, I do need 2 people that would be willing to just drive a short distance, like a mile, with 2 other students. Anybody just will do that? Okay, Sarah, and then one more person. Okay, we'll figure it out.
I also have a car, so I
Yeah,
can't.
okay, could you
But Sarah also. You both.
yeah,
So
well,
that's
I need
why
2 cars.
Oh, you need 2 cars.
Yeah.
I have
Sure.
a big car.
Oh, yeah. Okay, good.
Yeah, there we go.
Like a Hummer? A Hummer limousine. Okay, so
Sitting next to the
yeah,
table.
so
Guy.
Kira, and Sarah are gonna be leaders of 2 groups, and I'll tell you where you're gonna go. One group, you're just gonna drive basically across this little peninsula. There's a marina called West Bay Marina. I'll show you a map. Where's the marina? I'll pass this map because I'll show you what our plan is to do sampling to look at the mixing gradient of salt and fresh water. And we'll do it in the boat, but when you're in land, we're gonna do it around the peninsula. So I think I have 4, so each one for each group. So okay, you're head of one group, so that one, and you're the head of the other group, that one. And then I'm gonna pass 2 other ones just to circulate so people are aware of where exactly this is going. Okay, so just pass it around, but the leaders get theirs, and they can assemble the team to get started. Okay. So this little map shows kind of this orientation with you're here. This is you're here. In fact, the map is over there by the plaza, and then the north is over there. The seals are gonna chase you in the boat.
Yes.
They'll rock the boat.
That's what's gonna push you over, Ira.
South, that's north. And then you can see I selected 4 locations that go around the peninsula, right?
They're gonna take
One
you down
location
if
is
you
already
fall into
here.
the water.
So one team will actually have an easy job, which is just sample from here. The other team is going to go to Percival Landing, which is you just follow the water, and there's a public dock. You'll see there's a gate that's just spring loaded.
The playground.
Yeah, by the playground. Yeah, so that's the other one.
Oh, you weren't joking.
Come on over
This
here.
area.
And then the people are going to drive, and they're going to do the Swanta Marina, which has a dock furthest north that's public, that's unlocked. And then the last group is just going to go over across. This is called the Port of Olympia. On the side of Port of Olympia is the tip of the peninsula, and there's a restaurant there called the Heartfire. And then there's a little dock there too. Okay. So that way we'll get 4 stations around as the water mixes. And then each of you are also going to take your turns getting in the boat with Jenna. And we're going to sample 4 locations. 1 close to the bridge. That's the freshest water. 2 around here. Basically just across from the Port Plaza. And then depending on how much time we have, the last group probably just go, maybe at the end of the port of the peninsula. Right? Because we want to sample as the water mixes, fresh with salt water mixes. Okay. So that's kind of logistics. So we have two people that are going to drive with their groups to 2 locations. You have a view of what you're seeing. Okay, so what's my lecture going to be about? First, to give you the context of what we're doing here. We're doing this exercise. But how does it fit introduction to environmental studies, generally? And how does it fit global climate change? Okay? Then, I'm going to tell you why the estuary is so productive. I'll give a little lecture, but it's a continuation of it. I think in the lecture it was kind of broad stroke, so I'll give you a little more detail. And then I'll tell you what we're measuring and why. The report, if you get a chance to look at a handout, the report has basically 2 parts, or actually 3 parts. We're going to be like doing actual science, collecting data. So the first part of the report is simply explain in your own words why the estuary is so important. And I'll be lecturing about that today, so you'll be able to answer that. Why the estuary is so important? Why should we care? Okay, that's part 1. Part 2 is I'm going to tell you what we're going to be measuring, And I'd like you to explain why we're measuring those things. Each of the things that we're measuring gives us some information. So you should be able to say, why are we measuring this and the other. And as you do that, I want you to carry in the process of what scientists do is they create hypotheses. So before you do research, it's important to have a hypothesis, meaning you have a research question you're trying to address. It's good to have a hypothesis because that constrains, defines, determines what you're going to measure. And when you analyze the data, if the data matches your expectation, you have confidence that your knowledge of the system is correct. Very importantly, if it doesn't, as scientists, we appreciate that, because if it doesn't meet our expectations, then we know we need to refine our model. Right? So that's kind of how science progresses. So when you write papers, you never say something like, I don't know, I prove my hypothesis. It's really hard to prove a hypothesis because we're doing inductive reasoning. We're getting data to get to general principles. And you need a lot of data. So it's best to say the data supported my hypothesis or did not support my hypothesis. That way you're an advocate for the truth, not for your hypothesis. And that's an easy thing for science. You want to prove that there's global warming, so you go in with a hypothesis. There is lower. So if you come in with being vested under goodness of the data, that makes you less biased. Okay, so it's very important. Great. All right. So first, welcome to our classroom today. Is better or worse than lecture hall? Course 3.
Worse.
Worse.
Because it's colder.
It's cold. It's cold, right?
And there's no
And there's
water
no PowerPoint
in the lecture hall.
There's no PowerPoint.
The seal made it
Seal
better.
made it. Yeah.
It's
Seal
so
made it better.
cool.
The seals aren't cool.
No PowerPoint. You can project something on the fog. Like a PowerPoint presentation there. Okay. So, connected to environmental studies. So it's environmental studies. So I want to be able to give you a sense. If you do environmental science, what is to be outside? We're going to do this one. I'm going to go on the beach next week. So, regards to the weather, people sometimes get surprised when if you're a professional. This is you're really lucky. This is really good weather, right? To do sampling. You have to do it all the time. So one purpose is to get exposed to what it is to do environmental work, get a feel for it, how to do science, getting some data, matching it with a model, explaining if it fits or doesn't fit, things like that is part of doing environmental science. Okay? So we're doing environmental science related to global climate change. So some things that are relevant in this place. This is a coastal zone. It's a coastal zone. So the coast is going to be affected by sea level rise. And in fact, this time of the year, we have the kind of highest tides of the year, called king tides. It's a combination of the alignment of the sun and the moon, which occurs every month, but also the proximity of the Earth to the sun and the moon. There's a variety of factors that lead to what we call king tides. Also, when there's storms and there's changing atmospheric pressure and winds, that can also increase the tides based on the predictions. And today, let me pass the tides. I show you the tides in the handout, but they're really tiny. So you grab this and pass it around, take a look at it. And this shows you the tides today. So today, actually, this is a set of what called spring tides, because the sun and the moon are in line. So I think it's new moon. It's really dark. It's either new or full moon. So you can see the big red is low tides, so negative tides. In fact, last night the marine biodiversity class went clamming like at 9 at night in the rain. So you don't need to do that. Okay. So, but we are in the opposite one with the water column, so we benefit from the high tides. Okay. So look at the range from the low tide was like -3, and the plus is 14 feet elevation. Right. That's almost 5 meters. So I don't know how tall that is right now. How many feet do you think that is? Yeah. So it's like up and down, right? And then in 2 days. Today the high tide is gonna be like 14, or low tide, or high low tide is gonna be like 10. Just, we're actually gonna sample one of the low tides today, but it's not, the change is not very big. In 2 days or 3 days, it's gonna be 17 feet. Right, so there's danger of flooding in downtown Olympia. So another field ranger galoshes. So you can imagine the concerns, right? The city of Olympia has had people thinking of a long term is the remember the article relocate or what was it?
Or retreat.
Retreat, right? Retreat. But here is retreat or defend, right? So defend is, keep building up. Save us 300 years. So interesting, right? So note that as we're here, of the long range, not so long range planning, there's all this issues like even the flooding we're going to experience, and then if there's a storm event, it'll even be higher, right? So keep in mind that. Okay, so one important thing about understanding coastal system, its importance and its vulnerability is part of this class. That's why we're doing this. Second part is that you learn this cool thing about living things contribute to global warming over geologic time scales. And it's relevant today because biology is an important sink of carbon dioxide. So carbon dioxide is dynamic, so humans put it in, other natural process put carbon dioxide. It's a cycle. And it's important to understand the biological component of the cycle, because as we humans are affecting biology, they can also affect how much of the carbon is sequestered. So there's a lot of implications of understanding the biology to global climate change, short and long-term scales. The coastal zone, as I'll explain in a minute, is particularly important because it's super productive. It's an area where a lot of carbon dioxide is taken out. And it's also a place where a lot of the carbon dioxide that's put into biomass gets burned. So why do you think it's important that we are concerned about how much of the productivity in the world is buried?
The biggest tool for mitigating the CO2, what you buffering.
It's a way to think about a process that we could potentially manipulate to remove CO2 from the atmosphere. It's not a big one, but it's an important one, right? I'll tell you some other ones. Over the long term, on the geologic time cycle, the buried carbon in the coastal zone becomes oil. So that's like an interesting thing, right? So all the stuff that doesn't get decomposed, it's preserved, it's compressed, it becomes actually oil that we're using, right? So this oil is part of this long-term global cycle. Okay. But the major thing we're interested in today is this idea of productivity. By productivity, I mean biological productivity, growth of living things. And to focus on what part of that productivity we measure the base of the food chain, which is the primary production, photosynthesis primarily, right? So we're interested in photosynthesis and what controls photosynthesis in these areas. Now, estuaries, we're in an estuary, are among the most productive marine ecosystems in the world compared to croplands. Okay? So I'm going to explain to you why that is. Okay? First, the definition of estuary. Estuary is where fresh water meets salt water. Fresh water comes from the District River there. It's dammed, unfortunately. Unfortunately, there's a debate about that. So there's not a free-flowing estuary anymore because it's a dam. But we still get substantial mixing of fresh and salt. The ocean's over there. So, in theory, this area is actually very stressful for living things because they have to contend with big changes in salinity, which is not very good for living organisms. So in any hypothesis, I catch a lecture quickly about this yesterday, see how many people caught it, but any ideas of why this area is so productive? There's biodiversity too, but it's a consequence of the things I'm looking for.
The nutrients from the river.
Nutrients from the river, and then mixing. Okay, two important ideas. The river bring fresh water, but also bring fertilizers. Let's call them nutrients from now on, right? The nutrients are fertilizers, things that fuel photosynthesis. Okay? So they're a source of them because they erode land as they flow through, so they leach out the material goes into the water. And but the problem is that phytoplankton can't really use it because the river also brings sediment, minerals. They're floating. If you go to like Mount Rainier, you see the rivers. They're like, it looks like chalk, right? There's a lot of sediment. So that prevents light penetration. So even though there's lots of nutrients, they can't be utilized. So what happens to those sediments and those nutrients? They sink. Why? It's so cold. So the rivers are a little more turbulent, keeps stuff suspended. So when they come here, the sediment settles, but the nutrients are dissolved. So the nutrients don't. So all of a sudden, you have nutrients and you have like nutrients. Besides the lowering of the energy, because it's a protected area that prevents energy mixing, there's also salinity, and salinity creates separation of charges. So little particles acquire charges, they stick together and also settle. So somewhere in this gradient between fresh and salt, there is what I call the phytoplankton party zone. But don't write it in the exam or anything. Some people have done that. So. What do I mean by the party zone? Well, you have phytoplankton, you need two things to survive. You need three things. You need water, nutrients, and light. Well, there's plenty of water. You need nutrients and light. And usually in the open ocean, the nutrients are way in the deep sea. In here, they come from the surface. So it's great. But we'll have the problem with the sediment. So somewhere in here, the sediments are dropping off, and then the phytoplankton can grow like crazy. So there can be blooms of them here. I don't know here, it's winter time, so we'll see. All right. So in a nutshell, that's why this area is so productive. There's plenty of sources of nutrient. Light penetration is aided by the deposition of sediment. So you have big blooms, which can be fuel the. Okay, great. All right. So I'll give you a little bit for the first part of the report, basically explain that process, light nutrients and how they're maximized here. Okay. So let's talk about things that we're going to measure. We're going to measure with the Y size. If you remember, the yellow boxes have this instrument. And we're going to measure temperature and salinity. Why? Why should we care? Maybe, you want to give us
Temperature and salinity?
Yeah, why we measure temperature?
Because that'll determine, because we're looking for stratification,
Excellent,
right?
Excellent, right? So we did a whole lab on stratification, right? So stratification is analogous to if you're in a college and land, the first thing you do is map the terrain. Where's the elevation, where are the rivers. Here it looks like just a bunch of water, right? But now that you've done a stratification lab, as you know that salt and fresh, we're going to see their stratification. And where is it? We're going to map the system. Temperature and salinity. Okay? So very quickly, what are the hypotheses? What's going to happen to salinity as you go from the bridge out?
Dwindle.
Yeah.
Dwindle.
Yeah. Great. How about with depth? What's going to happen? More salty as you go. Excellent. Next one, temperature. Okay, so why temperature? Temperature affects density too. It's also important for marine life, but temperature doesn't vary that much in the water. But so more importantly, here in this case, it's going to be density. Okay. So a little bit trickier. Where's it going to be colder? Closer to the river or out at the sea? You think closer at sea? Why? From your experience. Okay. But how about any mechanism? Anybody can say why would it be further out there? Oh, bigger. Okay.
Circulation from the upwelling.
Sure. Maybe it's bigger. It's mixing, and if you learn from the lecture, water takes a lot of temperature. It takes a lot of energy to change temperature. Right? Whereas here it's shallower. I'll give you some other. It's good to have a hypothesis because you can test it. You can see if your reason is correct, and if it isn't, you adjust it. Right? As you go. So there's some complications, right? So we're in the winter, and it's shallow there, and it's been pretty cold. So if it's shallow, the cold temperature can cool the upper layer pretty quickly. Whereas a deep layer maybe still retains the heat from the fall and even the summer because it's kind of insulated. It's been there for a long time. So I'd be curious to see what we see. What you guys measure? If it's going to be getting colder or warmer? We don't know. I mean, it makes sense. Some people, another thing you could argue is that it gets heated from the surface. So if you go down with depth, it should be warmer in the surface and colder in the bottom. But keep in mind the concept of high heat capacity and the storage of heat and how long it takes for a water mass to change its temperature. So keep that in mind. Okay. We're going to also measure oxygen. Why do you measure oxygen? Good. Oxygen is a part of a photosynthesis. So in a way, it gives us an indication of photosynthetic activity. Right? So we'll use it that way today. So we'll see where in this gradient and with depth is the highest biological productivity. So that's one reason we're measuring oxygen. I'll tell you a little bit of the complication is that oxygen varies also with the amount of salinity and temperature. So we need to adjust for that, and I'll explain for that in lecture how we do that. But for today, we'll look at the changes in oxygen as an indication of photosynthetic activity. So what do you think happens with oxygen as you go with depth? Is the oxygen going to go up or down?
Down.
Down. Why?
Because you're
There's
deeper.
And
Oxygen's in the atmosphere.
sure, so air has 50 times more oxygen than water. Okay. So that's one reason. Another reason is that oxygen is produced by photosynthesis. So most of the photosynthesis on the surface, so that's also going to decline, right? Okay. Most of the composition is in bottom water, so oxygen should be less there. Great. We're going to measure oxygen. The next thing we're going to measure is the depth of light penetration, and then I'll have you guys assemble. There's some discs that we need the rope we need to tighten. So remember, you have this secchi disc, this pattern disc that you drop with depth, and then you raise it until you can't see it, and then measure the distance, right? So why should we measure the depth of light penetration? What information does that give us? Photosynthesis, more specifically, how much of the water column is light. So we want to do the calculation of the photosynthesis in an area. We need the surface, but then we also need the depth to get it's a three-dimensional system, right? Okay. So a question for you. So what should happen as you drop the disc? Should the disc be, the visibility get deeper or shallower as you go from fresh to salt? Why?
Density of salt, it's a little bit cloudier compared to fresh water, like the brackish, and then you get to the
Okay.
salt.
That's a good hypothesis that there's a difference in the light penetration between salt and fresh, but actually not that much. You have to, you have to be in the lab system. I just talked about one reason why the water clarity should be improving.
We're mixing the nutrients closer to the river.
Well, the nutrients are not, they don't absorb light, and they're going to be, they're high there, but and they're going to be flowing out, but that won't affect light penetration. The sediment, right? The sediment.
That's what I meant, like the stuff of the water.
Yeah. But remember, there's two things. The stuff is particulate, which is sediment that settles, and then dissolve doesn't sink, right? Okay. And then, so in theory, it should be getting more clear as you get out. But sometimes you don't see that, especially in the spring. That's a clue. In springtime and summer, as you'll get deeper. And somewhere in here, it'll get shallow again. All of a sudden, you put the secchi disc and like, oh, I can see it already, So what could explain that? It gets deeper as you predicted, and then all of a sudden it gets shallow.
River flow, ice melt.
Well, but how would that be? The ice melt and river flow is coming in, right? The sediment settling.
Yeah.
So it shouldn't be settling more and more and be less sediment as you get out. Yeah, certification wouldn't
Maybe
be.
like the waves and the current pushing it back.
That's a good hypothesis. The sediment could be resistant and moved around. But typically, once it settles, it's stuck in the seafloor. What else absorbs light besides silts and clays?
Kelp.
Close. What's smaller than kelp?
Algae.
Algae.
You're good.
Yeah. Oh, okay. So imagine what's happening. Okay, so there's nutrients and sediment. Photosynthesis can't really occur because it can't get enough light. Then all of a sudden the sediment settles. There's lots of nutrients. So what happens to the algae? That's the party zone, right?
Yeah.
So the party zone could be a place where the secchi disc shallows. How would we know if the shallowing is due to sediment and not something else?
Looking at the water.
Yeah, so we'll take a plankton sample. We're gonna take plankton samples, and then probably we'll take a look at them in the microscope. We can measure the amount of chlorophyll and figure it out, or we can do the oxygen. Right, the oxygen should also reflect that if there is a bloom, then we know if the peak's associated with oxygen, then it's a bloom. Right? Great. Okay, great. So yeah, you know what we're gonna measure. Then you are gonna take measurements. You're gonna give me all the data, and then tonight I'm gonna compile it, and I'll choose the best data. The boat data. By best, I don't mean like fudge data, because we want to answer the question what happens as the water mixes. Right? So there's two ways to see it now: along the shore or on the boat. Right? So I'll give you one of those two to analyze. I'll give you both, but you choose one. I'll tell you which one, because then they'll all be consistent for the discussion. Okay. And then once you get the data, all you need to do is basically test your hypothesis. Did it match or not, and why? Got it? Okay. So you have, at this point, you could already write the first part of the project, the report. Great. Okay. So let's start moving so we don't get too cold. So form the people that are driving, get two other people.